Theorem on a linear transformation. So first of all we are going to write a statement. Let T is a mapping from vector space V to vector space W is linear transformation. Then prove that or show that number 1, the kernel of T is subspace of V, and number 2, range of T is subspace of W. So prove, first of all, what is given part here. The given T is a mapping from V to W is linear transformation. And what is claim here? Claim 1, kernel of T is subspace of V. Now, so as we know that since T of 0 bar is equal to 0 bar, and why 0 bar belongs to V? Because V is a vector space, and therefore this implies 0 bar belongs to kernel of T, and therefore this implies kernel of T is, this set is not empty. Now let for any two vectors, say v1 bar and v2 bar from V belongs to kernel of T, we want to show that v1 bar plus v2 bar is also belongs to kernel of T. Now since v1 bar v2 bar belongs to kernel of T, this implies T of v1 bar is equal to 0 bar and T of v2 bar is equal to 0 bar. Why? Because by using definition of kernel. Now consider T of v1 bar plus v2 bar is equal to, T of v1 bar plus v2 bar is equal to T of v1 bar plus T of v2 bar. But what is T of v1 bar? It is equal to what? 0 bar, and here it is what? 0 bar. So this is equal to 0 bar plus 0 bar, which is equal to what? 0 bar. So this implies T of v1 bar plus v2 bar belongs to is equal to 0 bar. This implies v1 bar plus v2 bar belongs to kernel of T. So if v1 bar v2 bar, what? Any two vectors from kernel of T, and their addition is what? Belongs to kernel of T. So kernel of T is closed under, therefore kernel of T is closed under vector addition. Similarly, let for any scalar k, and for any vector v bar belongs to kernel of T. Now since v bar belongs to kernel of T, this implies T of v bar is equal to 0 bar. Here say since T is a linear transformation. Now consider T of k v bar, since it is equal to k times T of v bar. Why? Because T is linear transformation. But what is T of v bar? T of v bar is equal to what? 0 bar. So this is what? K times 0 bar, but k times 0 bar is what? 0 bar. So T of kv bar is equal to 0 bar. This implies k into v bar belongs to kernel of T, and therefore kernel of T is closed under vector under scalar multiplication, and therefore okay, so it is closed under vector addition and closed under scalar multiplication, and therefore kernel of T Since kernel of T is subset of V, kernel of T is subspace of V. Now the part 2 here. Now suppose in the part 2, what is given again? Given T is a mapping from V to W is linear transformation. On what is claim here? Claim say 2, range of T is subspace of W. Again, now since T of 0 bar is equal to 0 bar, and therefore this implies 0 bar belongs to range of T, and this implies range of T is not equal to phi. Again, why 0 bar? This is what, since V is a vector space, therefore 0 bar belongs to V, and T is a linear transformation, therefore T of 0 bar is equal to what? 0 bar. Now let W1 bar and W2 bar be any two vectors from a range of T. So this implies there exists, by using definition of range of T, there exists vector V1 bar and V2 bar from set V such that T of V1 bar is equal to W1 bar and T of V2 bar is equal to W2 bar. This is again by using why this is exists such a V1 bar V2 bar, because by using definition of range of T. Now since V1 bar and V2 bar belongs to V, and V is a vector space, this implies V1 bar plus V2 bar belongs to V. But this belongs to V implies if we apply T on V1 bar plus V2 bar, it belongs to range of T. But T is a linear transformation, so this from this we can write T of V1 bar plus T of V2 bar belongs to range of T. Why this? Again, since T is a linear transformation, this implies T of V1 bar plus V2 bar is equal to T of V1 bar plus T of V2 bar. So, but what is T of V1 bar? Here you can check. T of V1 bar is W1 bar and T of V2 bar is what? W2 bar. So this implies W1 bar plus W2 bar belongs to range of T, and therefore range of T is closed under vector addition. Now let for any scalar k and W bar belongs to range of T. Now since we want to show that KW bar is also belongs to range of T, so since W bar belongs to range of T, this implies there exists a vector V bar belongs to V such that T of V bar is equal to W bar. Now since V bar belongs to V and K is any scalar, say K is any scalar, this implies K into V bar belongs to V. Why? Because V is a vector space. V is what? Vector space. So it is closed under scalar multiplication. Now since KV bar belongs to V, this implies T of KV bar belongs to range of T. But again, T is a linear transformation. From this we can write K into TV bar belongs to range of T. Why? Since T is a linear transformation, T of KV bar is equal to K times T of V bar, and therefore, but what is TV bar? TV bar is what? W bar. So K into W bar belongs to range of T. So for any scalar K and W bar belongs to range of T, their KW bar is also belongs to range of T, and therefore range of T is closed under scalar multiplication, and therefore uh, now therefore since range of t is not empty, first of all range of t is not empty, range of t is closed under vector addition, and range of t is closed under scalar multiplication, and since range of t is a subset of w, and therefore range of t is subspace space of w, hence the proof.